vectors with inputs, we are going to do convolutions on vectors. And so we extended the architecture, DPCN architecture, to a dynamic convolution model. Basically the same. I'm not going to get into details because they get a little, the explanation gets a little more complicated. But this is how you write the observation model with convolutions. It's basically the same thing. So I'm going to have to sum is a sum of a matrix of coefficients. Now I have convolution filters, right, with the states, and then I will have a noise term. And if I pass this to the other side, I also would like to minimize n. And likewise, I can do the same thing for the state equation using convolutions. All right. And for object recognition, I'm going to impose a condition that the terms in the diagonal of the model are going to be exactly 1. Because I like to represent input. All right, so I'm not going to go into I can also rewrite the equations. You know, this is all in a paper that was published 2 years ago in Transactions on Neural Networks, if you want to see the results. Okay, so I'm going to just tell you, give you a little example with a movie. This is the training of so the model was presented with videos of 16 people that are talking. So this is video TIMID, it's called TIMID database, because people are talking at the same time that they are being filmed. And no labels. We just present this concatenation of videos to the model, and we monitor the training by looking at the causes of a 2-layer model. Now I'm going to have 2 layers. One, so is the concatenation of 2. The hierarchy is order 2, and we monitor the training by projecting the 60-dimensional causes of the last layer onto the principal component space. And so in the beginning of training, the representation of each one of these movies, starts in the center of the space, and then they diverge through training. And so this is color-coded. One of the different colors is for one of the pictures, and you see the figures, and you see that the model really is able to discriminate in an unsupervised manner all these 16 people. And if I want to see what the model learned after training, this is basically now is with the convolution network, but you see basically the same type of receptive fields that we saw for the pixel-based system. Look at the first layer causes. You are already putting together these receptive fields, in it seems kind of characters, graphic characters. But if you go to the second layer causes, you see that these kind of seem like gestalts of the different figures. So the model was able to come up with distinctive features from all these, 16 persons, and it was able to capture them in this representation. This representation, in order to get this picture, what I have to do, I have to get the causes and then propagate them back through the trained network. Okay? So this is the reason why I can get these very nice pictures. But if you look at the states, you are not going to see anything. So I'm going to give you an idea of exactly what is when the model was trained. After it was trained, then we start seeing how robust these features were. And this hopefully. Problem. I don't know how to control the video. All right. Maybe I go there and play the video, because I think it's very nice for you to see. I have to come here. All right. So this is the model trained. Parameters are fixed, and then I include this occlusion that moves around, and I like to find out if the model still is able to discriminate the 16 people. And I'm showing to you the states in the first layer, the causes in the first layer, states on second layer, causes in second layer. And I'm representing also for you the internal representations on the top layer. And it's very interesting that you see that when in the first layer, when a feature is activated, it's very short in time. The causes are activated longer. And at the second layer, you really have very long activations. And this time of this vector, so you can think that you have here a 60-dimensional vector, this is the representation of each person. Okay? And of course, the model is not able to get rid of the occlusion, but I told you that I have that top layer, right? The top layer is an extra input to the network. And what we decided to do is to use the causes of the previous frame and input to the, to the current frame. And it turns out that this simple modification stabilizes the internal representations of the network, while the input data changes drastically. See, this occlusion, was extracted out by the system because of the dynamics. So you see, the dynamics are helping you make decisions in space, right? So time is important exactly to give you information about state. And so this proves really that what we should be thinking of is getting invariant representations and not care very much about what happens in the input space. Right? Now this is, I think it was very interesting, a very interesting conclusion. Of course, we also, I'm not going to go into detail, but we compared the performance of our method with other methods, mostly deep learning methods, and it's compatible. Both in the coordinate 100 data set, the UCSD data sets, and the celebrity face data set. And we have representations that are very similar, or performance there is very similar to the best neural network out there. But of course, these data sets are still very, very small. And so the scaling up of the model is a problem. So what can I conclude from what I told you? First, DPCN, this generative modeling, is an alternative to backpropagation to learn and supervise information transfer. They are not using really the decoding as everybody does in machine learning. Inference is expensive. This model always is doing inference, even during testing. So that even with the parameters fixed, X and U are being computed, have to be computed at every step, okay, through an optimization. So this really is the reason why this system generalizes pretty well, but this computation is very, 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 very expensive. And I don't think that DPCN does not take full advantage of the bidirectional architecture. I just give you an example, of how we could use the causes from the previous frame. But I think that this is really the unexplored part of this architecture. I can bring information, for instance, from an external memory, and also change the way that the system is extracting information from the input. And so, in terms of a machine learning framework, so the thing that I think we need to start thinking, of course, if you are not Google, if you are Google or Facebook, you have all the computers on the web, you don't need to be efficient, right? Because you could force it. But the problem is, most of us have, small clusters in our labs, we have to be efficient. So we have to go beyond this brute forcing technique of getting all the data in the world to be able to train our models. Anyway, but this is a very important question, because how do you break this huge joint probability of image, of pixels, of models, and of locations in an image? So to do scene and understanding. This is really the fundamental problem that we have to worry about. And if we go back to the brain, you see, the brain, we think that we see the world, you know, in full resolution all the time. It's wrong. We use full field vision. We only see 5% of the world at full resolution at every time. And then we say, okay, we go to another part of the space and then we reconstruct. Okay? So the brain itself, you know, is unable to deal with this flow of information from the visuals that come from the retina, and it uses techniques, you know, shortcuts probably, to effectively be able to handle all the information. And so there are two paths in the visual system. You know, the ventral path that really answers the question of what is in the image, this particular focal point is. So there's the what path, and then there's a where path. And this where path is one that really has to get information from the frontals, you know, where you have the executive model that is telling you what are the next steps that the system should be doing, and to exactly control the saccading in the eyes. And also this dorsal path is the path that tells you the information of where things are in the visual field. Okay? And so the hypothesis is by combining a fixation in the saccade system with an object recognition system such as the PCN that I showed you, can we create a next visual vision system? So basically what I'm saying is that if I look at how the brain handles the processing of the imagery, the brain uses a decomposition of a joint in a product of marginals, and one of the marginals is exactly what are the objects, you know, the other marginal where they are, and of course this is the computation that you have to do to effectively compute the prior. So this is basically what we also implemented. We came up with a human-inspired scene understanding. We take an image, we fixate in a small region of interest, and we create a video from that particular portion that is foveated. And then we send the video to the DPCN, and the DPCN finds out what is exactly that particular patch, what is the information that is contained in the patch. The advantage of this is that we can go back to, you know, to pixel-based computation. We don't need to have this very large convolution network. And we implemented this with a litro camera. The beautiful thing about the litro camera is that it blurs the world depending upon the way of the focus. Okay, so you see, if the litro camera focuses in this person, you know, in this image, you know, all the others are blurred. And so the first step that we have to do is we have to come up with a focus of attention. I'm not going to get into this because this is, you know, we use the gamma focus of attention, but there are many others in the literature for saliency detection. And the reason why we decided to go with the gamma is that it's a recursive computation. It's very fast, and we get basically the same performance as all the others. You know, so I'm not going to get into the details. But the computation time is very fast. Okay, so I'm going to. Oh, I have to go there again because I like to show you what is for this scene what the human observers do, and the computer with the saliency is able to do. I have to come here. Okay. Yeah. So this is the focus of attention of the human observer on the picture that I showed you, and this is exactly what our system does. Of course, we tell the user look at the numbers, and of course the user just looks at the numbers. But our system has not that information, so it does not have top-down information. It's going only bottom-up, and makes a mistake. But this is just to show you how the system is doing, and I'm not going to. And then we patch here the focus, the area where the foveate region. We patch it, and we send each one of these little patches to the DPCN with a certain organization. I don't have time to go into the details. We tested this in a Clutter MNIST data set, and the results are so let me explain a little bit how I created the imagery. So the MNIST is 28 by 28 benches with the number, and we created an image of 60 by 60, and we included noise from 6 by 6 crops of digits. So we have this, imagery, composed imagery, and the idea is to use our Foveat system to find out exactly where are the numbers and to recognize the numbers. And this is totally unsupervised. And so this is what the DPCN full, if I present the 60 by 60 image, this is the performance. The performance is not very good, but if I put the Foveat region, the focus of attention, the improvement is very good. So this is unsupervised, right? If I use a CNN with labels on the full image, because this is a noisy image, this is the performance that you get. But of course, if you put a focus of attention on the CNN, the performance goes much higher. Okay, so you see the Foveat, the idea of using a focus of attention is it can be implemented in any system, not only in our DPCN, you can also do the others. This is the spatial transformer network that is all supervised, and it gets very good results for this. But remember that these numbers that you see here are totally unsupervised. And then we went to the big test, is the street view house numbers. This is a data set that was collected by Google. And the results on this data set for now are all including just the bounded digits. So someone has to go there and find what the digits are, and then the system can tell you exactly what are the numbers. Okay. We are interested in using the Foveat system without the bounding digits. Okay. So I'm presenting each picture in the Google Street View for our model. And these are the results. The results are that the unsupervised model, the autoencoder, of course we didn't put a focus of attention on the autoencoder, but the autoencoder for this problem is pretty bad. And the DPCN works with the Foveat works relatively well, but look at the computation time. So this is huge. So you are trading here labels by computation time, as you can see. But the results are really comparable with the CNN full. Okay. Of course, if I put the Foveat system on the CNN, the improvement is higher. Okay. But this is just to tell you, that this idea of breaking the joint distribution in this way that was reminiscent from biology makes a lot of sense. Okay, so as conclusions, I think that the predictive coding appears powerful enough to self-organize sensory processing on real imagery. And I think we need to go back and learn much more about cognitive science and try to encapsulate this knowledge in mathematical formulas and architectures that really can help us solve some of the problems of vision, that are very, very complex. We have not explored yet fully the top-down architecture, because the causes can be brought, for instance, from memory, and in order to do that, we have to really extract events in time, something that we have not done yet, and nobody that I know has done the extraction of events in time in automated means. But I think we are getting closer to autonomous vision, and finally to implement the definition of perception, something I would like to see if I can do. I don't have too many years to do it, so I have to be efficient. Thank you very much for your attention.
Thank you very much. Questions? Maybe I can and stay down. Yep.
Hi, I love your talk. I'll read your papers. My question is, okay, so the brain may not use back propagation, but you're still using gradient descent on very standard cost functions. And your cognitive circuitry is probably implemented on cortical microcolumns, where the computing units communicate using delta functions. So my question is, how do you get gradient descent out of delta functions?
That's a very good point, and there's been work, not only from my group, from other groups, Graves, has the neural Turing machine that basically uses the same ideas. You can come up with approximations of, for instance, the delta function. Just think of a Gaussian, a very, very, slim Gaussian. You still can differentiate it. It's an approximation, but effectively this is what we are using right now in the models.
Thank you.
But it's a very good point. Let me say that it's a very good point, because you see, if we want to create a learning architecture with current formulations that we have, everything has to be differentiable, right? Because if I want to do optimization and using simple techniques like gradient descent, I can go to subgradient, but then the problem becomes so much harder, that I think we have to stick with smooth functions.
So I have two short questions. One, when you look at the foveating algorithm, so you're doing amazing when you take the foveating information and put it into the algorithm. How similar people are to each other that you can say that's how people do?
Yeah, I mean, so the problem of foveation, I think, has not been posed in its complete manner. Because foveation, I think, has two sources of information. The bottom-up information that is associated with high contrast regions, but also the intent of the user, right? So the intent of the user, in my model, what we are trying to do is use the intent, the top-down, as a prior that will change the saliency that comes bottom-up. You understand? And so your question is going to be very difficult to answer, right? Because different persons probably are going to have different top-down information, right? And so presenting in even the same person, if you ask on a given scene, if you ask different questions, you are going to end up really with different foveation areas, right? This is very, very interesting. We already have tried this, and for instance, in that image that I told you, I can put the top-down information. I have not shown those results, but we already have them. That suppose that I say I want the numbers in ascending order. So just this idea of giving you ascending order is going to change what is more salient in the input space. Okay, so this is very interesting.